So yesterday we saw two examples of the reduction of order method as used to find a second linearly independent solution to a second order homogeneous ODE. While we were doing those examples, there were a lot of steps that we ended up doing sort of multiple times. In both examples, we did product rule in total 3 times to find out what y prime and y double prime were equal to. In both examples, we plugged in those expressions to our differential equation and simplified and combined like terms. In both examples, if we'd done our work correctly, then the u of x term always vanished. And then, in the second example in particular, we did a change of variable that allowed us to first calculate v equals u prime and then integrate that to find u. Now, in situations where you find yourself working multiple example problems and kind of doing the same steps over and over again in the example problems, there's usually a formula that can be used to capture those repeated steps and keep you from having to do those repeated steps over and over and over again. And that's what we're going to introduce today. We're going to introduce a reduction of order formula, a shortcut formula that allows us to skip doing those steps that we just did over and over and over again yesterday in the video and in the exercises. Now, to begin with, before you even get started using this formula, you need to rewrite your differential equation in the proper format. If you're going to use this formula, you need to rewrite this expression so that y prime stands alone. Once you've done that, you're left with a differential equation that has y double prime by itself, a function of x times y single prime, and a function of x times y equals 0. Now suppose that you have a solution already called y1, and your goal is to find a secondary solution called y2. So let's proceed with the usual guess that y2 is equal to u of x times y1. Okay, as always, we're going to begin by finding an expression for y2 prime, using, as always, product rule. First times the derivative of the second plus the second times the derivative of the first. As always, we're going to use product rule again to find an expression for y double prime. So here we have the first times the derivative of the second, plus the second times the derivative of the first, and then again the first times the derivative of the second, and then the second times the derivative of the first. Just as before, we end up with two terms that can be combined in this expression, 2u prime, y1 prime. Once again, we're going to do exactly the same thing that we did yesterday. We're going to take these expressions and plug them into the differential equation. So instead of y double prime, I'm going to lead with ux, y1 double prime, 2u prime, y1 prime, u double prime, y1. Then, for the next term in the differential equation, we have y single prime multiplied by the mystery function p of x. So p of x times u of x y1 prime plus u prime y1. We also have the mystery function q of x times the original y2. So q of x, u of x, y1, and that needs to be equal to 0. Now the next thing that I'm going to do, just as in our previous exercises, is I'm going to multiply everything out and try and combine like terms. And as I'm writing down what I get from multiplying this out, I'm going to try and arrange it based on which terms have u of x, which terms have u prime, and which terms have u double prime. For example, I get u of x y1 double prime from the very first term, and then in green in the second line I get plus p of x u of x y1 single prime, and I also get a u of x term from the third line, q of x u of x y1. Now I'm going to check which terms have a u prime in them. I get a u prime from the second term in the first line, 2u prime, y1 prime. And I also get a u prime from the second line, p of x, u prime of x, y1. Finally, there's only one term with a u double prime in it, u double prime of x times y1. Now, have a look at this first line. Because all three of these terms have a u of x in it, that u of x can be factored out. Likewise, in the second line, the y prime can be factored out. And then in the third line, we just have the single term, u double prime of x, y1 is equal to 0. Now remember, yesterday, we said that if reduction of order was done correctly, that the u of x term should always cancel out when we combine like terms. And the reason for that lives in these blue brackets. Notice that what we have in the blue brackets is exactly the same thing as the left-hand side of our differential equation. Y double prime, p of x, y prime, q of x, y. The left side of our differential equation with y1 in y's position. Now because y1 is a solution to the differential equation, when I plug it into the differential equation, as I have done here, the result should be equal to 0. So that means that this blue line completely vanishes, and all that's left is the u prime term, u prime times 2 y1 prime plus p of x, y1, and the u double prime term. Now because the u term has vanished, I can do a reduction of order by letting v equal u prime, so that v prime is equal to u double prime. And this changes my equation from being second order to being first order. And just as in yesterday's second example, when I do this, I end up with a separable differential equation. I'm going to do a little bit of rearranging here. Let's move the term containing v to the right side. And then separate our variables so that we have 1 over v, v prime, is equal to negative 2 y1 prime divided by y1. And then when I divide the second term by y1, the two y1s will cancel, and I'm just left with negative p of x. So now let's go ahead and let's integrate both sides. As we know, when we integrate the left-hand side, that's just going to become the natural log absolute value of v. Now let's see what we can do with the right-hand side. There's not much we can do with p of x, which is just a complete mystery function. So all I'm going to do is write it as the integral of p of x, whatever it happens to be. But there is something actually that can be done with the integral of this fraction here, y1 prime divided by y1. As a rule, if you take the integral of the derivative of a function divided by that function, the result is always equal to the natural log of the absolute value of that function. So if I integrate y1 prime divided by y1, the result of that is just going to be equal to the absolute value of y1, natural log. I'm not going to bother with the plus c. We're just trying to find the simplest, we're just trying to find one possible value of u of x, one possible answer, and so I don't have to worry about plus c, which gives us all possible answers. Now I'm going to exponentiate both sides. And I'm going to use a few properties of exponentials to simplify this. This says that v is equal to e to the negative 2 natural log absolute value y times e to the negative integral of p of x dx. And if I simplify this first e, this becomes y1 to the power negative 2 which in turn can be rewritten as a division by y1 squared. So this is what v must be equal to, and therefore this is what u prime must be equal to. So in sum, if you want to do the reduction of order shorthand formula, you start by writing your differential equation in a format where y double prime stands alone. Then you figure out the value of this expression on the right. That is equal to u prime. And finally, you can find u by integrating. Let's go ahead and see this formula in action in the following exercise. We're given the ODE x squared y double prime minus xy prime plus 2y equals 0. Someone did the work and figured out somehow that x times sine of natural log of x was one solution to this equation. So let's go ahead and figure out the other solution so that we can completely solve the ODE. Now before I use the formula, I gotta make sure that the ODE is written in the correct format, which is that y double prime has got to stand alone. That's not what we have currently. We have an x squared in the way, so let's first divide out that x squared. This reveals that our actual value of p of x for the purposes of the integral in the formula, p of x must be equal to negative 1 over x. So if I calculate e to the negative integral of negative 1 over x, then this is equal to e to the natural log of x. Once again, I only need one non-constant value of u of x, so I'm just going to take the simplest possible antiderivative in every step of this calculation. So in my formula, the numerator has worked out to be just x, and so the value of u prime must be equal to x in the numerator, and then in the denominator we have our y1 squared. X squared sine squared natural log of x. So in order to determine the value of u, I need to figure out what is the integral of 1 over x times moving sine squared out of the denominator, changing it to cosecant squared natural log of x. Now, believe it or not, this antiderivative can actually be calculated by hand. If I was in a very perverse mood, I would give this to my Calc 2 students. You can actually evaluate this by using a substitution. Now, I can't use a u substitution because u is already taken, so let me just go ahead and let t be equal to the natural log of x. That way dt is equal to that 1 over x dx that we have in our integral. So u is equal to the integral of cosecant squared of t dt, and the antiderivative of cosecant squared is just equal to negative cotangent. So, if that's our value for u, our second solution must be equal to negative cotangent natural log of x multiplied by x times sine of natural log of x. Now when you have sine of something times cotangent of something, that can be simplified to just cosine. So our second linearly independent solution, the sister to the one that we were given, is x times cosine natural log of x as opposed to x times sine. So what's our general solution to the ODE? What do all solutions look like? They look like c1 times x sine of natural log plus c2 times negative x. Why not? Let's just put the minus sign here. X cosine natural log. Now the minus sign really doesn't matter because c2 can be either positive or negative, so we can sort of roll that negative sign into c2 and refresh it into a new coefficient if we wanted to, but it doesn't really matter too much either way. That is the shorthand reduction of order formula as applied to this example. This is absolutely a perfect example for the shorthand formula because in this case our y1 was so complicated. I would really hate to think of doing the process, the long form process of reduction of order with a y1 that was this involved. So this is a perfect opportunity to use the shortcut. That concludes today's material. We derived a shortcut formula for reduction of order that could be used in more complicated examples like this one. Really, the only thing that you need to look out for is to make sure that when you employ this formula, your ODE has been rewritten so that y double prime stands alone.